Today we will see how to manage shader animation, and specifically how to control activation, deactivation, and timing of a shader in Godot 4. We will create the sample animation using different techniques, depending on the shader's level of autonomy. Since the shader runs on the GPU, the more things it can do on its own, the less the CPU is involved, thus reducing CPU load and GPU interruptions. First, we will animate a non-autonomous shader step by step in two different ways, using an animation player to modify material properties, or using a tween to modify shader parameters. Next, we'll control a slightly more autonomous shader, manipulating its timing directly via script. Let's go to the project. The mesh of our sample ray is essentially made up of two segmented orthogonal strips. Initial material is set with the non-autonomous shader. Thus, excluding the noise, it can only be animated by changing its parameters. In the scene, there are also a fake generator box and an activator, which will control the shader animation via script. The fire function is invoked every time the activator bounces off the generator. Now let's add the animation player. This way it can't restart if it's already playing, so we need to stop and restart. Very easy to set up even for predefined complex animations, but static in the main. On the other side we have tween, which can instead be easily created and set dynamically as needed. Oops! Too dynamic. I missed to set the initial value of the parameter. It could never repeat the animation without a reset. And we can also simulate the recharging effect seen before. That's it. Such a shader needs to be continuously fed by the CPU, and it should be avoided as much as possible, because the GPU can do the same job better on its own. Well, it's time to move on to a bolder shader. A shader which never has to ask. Since spatial shaders can have neither inter-frame memory nor output parameters, an autonomous spatial shader can only rely on context parameters, like time. We could also create a compute shader that feeds the spatial shader, but except in very specific cases, this is not an option to relieve the CPU. Our new shader can animate itself by leveraging time, and since we need to control it from the outside, we need to force the start time of its animation. Here's how. Something is odd. The animation seems to start with some lag. Shader time may possibly not being synchronized with engine time due to some delay on startup. If this is the case, simply picking a time closer to the real shader's start time would fix the issue. Let's try using a static variable, which picks the time when activator is initialized. Okay, better. But we should also consider the additional delay caused by the process function. Because even if the function is invoked at regular intervals, it is not exactly at the moment of activator contact. So, now we have a rough solution and a new mystery. Why the lag, and how much is the shader clock delay? Only the spatial shader can tell, and it is usually a quiet type. So we have to break the rules, open a tier-way communication with the shader and wait for the response. In order to do that, we can read the shader output by turning it into a texture, using a subviewport. To make things easier, we will use a canvas item shader to write into a two-dimensional texture, not exactly a spatial one, and even with a different code, but we can try it anyway. The Canvas item shader also has the same delayed behavior as expected. You can see it by the green coming in late. Yes, we found the exact delay duration. The lag is likely caused by the shader compilation phase and can be measured using the shader itself. I'll use it instead of the previous value. So we can write a simpler initialization code which computes the delay and turns off once the data is ready. You can find it on GitHub. See you in the next video. Bye bye.